again. Welcome to another A-level chemistry video. It's going to be about alkanes, but just before that, if you want to keep up to date with everything that I'm doing, make sure you subscribe to the channel. Right, alkane reactions. Not a lot to say really. The rest of the organic stuff, far more exciting, lots of reactions going on, but it starts with alkanes. Alkanes is where it links to GCSE up to a fair degree. So there's this top formula is something that you should be familiar with. This is the GCSE's general formula for alkanes. Double the number of carbons and an extra 2 for the number of hydrogens. But we need to take it a bit further. So when we go to cycloalkanes like cyclohexane and all the other ones, there's 2 hydrogens less in order to close the ring round. So the general formula becomes CnH2n. So what is really important is not this formula, although it helps to know it, but it's the fact that it's saturated, meaning there's nothing else but single bonds between carbon and carbon and single bonds between carbon and hydrogen, meaning there's as much hydrogen as you can have. The overall picture is that the reactions are not particularly involving in terms of the chemistry. There's much more involving reactions to come in the videos about different functional groups and different types of compounds. There are 4 reactions. I'm not going to go into some of them in any detail really, particularly, well, a little bit of detail. Combustion, we'll have a look at a little bit about combustion, because combustion comes in the 2 halves of incomplete and complete combustion depending on the supply of oxygen. Cracking is a GCSE content and it hasn't changed at all. You may well know enough about that already, but we'll have a quick look at a little bit of that. Reforming is perhaps new, but it is what it says. Take well, usually it's an alkane, reform it with a catalyst. Reforming means get it into be something else that it wasn't in the first place, which is the basis of a lot of reactions, I suppose, but it's a particular type of change. And the real important one, because this is way ahead, the most important in terms of exam questions, is new to A-level, and photochemical substitution. So we'll definitely be looking at that. In fact, it's going to get some detail today, and there's another video already on the channel about how this takes place. I'll talk a little bit about that when we get to photochemical substitution, because it is the major focus of what we're trying to get across to you today. So the picture is not much to consider. These are fairly straightforward reactions. This is the important A-level one, and I'll see you when I'm ready for the next bit in a moment. So let's just have a little, it's kind of pretty much a recap of combustion. 2 sorts of flame colour, a yellow flame colour or a blue flame colour. Bunsen burner. Close the air hole, yellow flame. Incomplete. When it's a blue flame, when you open up the air hole on a Bunsen burner, complete. So that's how Bunsen burners work. You open up the air hole, you get more oxygen supply into the gas coming through the gas pipe, and you get more complete combustion. As a result, you get a hotter flame. So here you get less energy coming out compared to this energy that comes out of here. So when you look at the equation, when this is complete combustion, where the only products are carbon dioxide and water, that gives you the maximum energy out from the combustion, which is why we burn fuels. Incomplete combustion, when you have a yellow flame, is more inefficient. Energy doesn't come out so well. Lower temperature flame makes it yellow. When you burn most alkanes in air, the flame is yellow. When you see those special effect things in films of things colliding, there's a big wall new word, of yellow flame. Incomplete combustion. And you'll probably cough when you're doing it. It's a big burst of yellow flames, incomplete combustion. Blue flames, hotter but not so exciting to look at in films, I think. So they'll be burning an alkane. If you look at things like octane that is what cars run on, or petrol is octane anyway, not diesel. It's incomplete combustion. When you burn octane itself, it's really sooty. You can see the streams of smoke coming off of it. It's very much incomplete. So it's not common to find alkanes burning it complete. The only one you can really get to burn complete is methane, which is it's a good job really, because you don't want carbon monoxide in the atmosphere where you're working. Just to recap what the products are, if you do complete combustion, there are only two. The hydrogen gets turned into water and the carbon gets turned into carbon dioxide. Maximum taking in of oxygen in order to do that. If you get a yellow flame with incomplete combustion, it's not that you don't get these two. In fact, all your hydrogen still turns into water because there's no other options. But not all of the carbon dioxide is formed. You get the toxic CO, so yellow flames produce carbon monoxide, so therefore you don't want to be in a room with yellow flames for a long time unless the exhaust is leaving. And you also get solid carbon, which is the visible smoke, sooty smoke that you can see. If you put a piece of glass in a yellow flame, it'll come out sort of smoky glass which has got particulate carbon on. In fact, the flame is often not hot enough to burn all the fuel, and you get unburned fuel as well. So MOT tests for a car, not an electric car obviously, but MOT tests for a fuel burning car, it monitors the level of carbon monoxide, and it also monitors the level of unburned fuel, which is obviously not part of the reaction. You can write balanced equations for this. You can't for this because this is very much conditions dependent. There are too many variables in that for it to be the same every time. This one you would have to have for complete combustion. You'd have to enhance the amount of oxygen that you've got. You'd have to increase the concentration of oxygen around the alkane. This one here is what takes place at 21% as you do in the air. So here, ideally you burn it in an atmosphere of pure oxygen, then you're guaranteed to get complete combustion, but you can do it just by increasing the level of oxygen to, I actually have no idea, probably 60% or something. Standard air combustion, yellow flames, special effects in films and so on. Right, I'm going to do how you balance complete combustion equations, because there's kind of a little tip to it that makes it easier to balance. I'll see you in a moment. So complete combustion equations. These are obviously not balanced, I've got any numbers in at the moment. The tip is the following, first of all, that instead of going, oh, how many have I got? Oh, how many have I got on each side, which is the standard way of balancing things until you know a few other ways. No, all the carbons are going to turn into carbon dioxide. 5 carbons, this is pentane, it's a liquid, going to get 5 CO2. All the hydrogens turned into water. Got to be H2, so there'll be 12 hydrogens can only produce 6 waters. Then, how many oxygen pairs have you got? 5 oxygen pairs in the CO2, and then 6 oxygens in the water. That's another 3 pairs. 5 and 3, 8 O2. The second tip is that most of the expected equations are for 1 mole of the combustible substance. So 1 mole of these are alkanes. So there's butane. Butane is a gas rather than a liquid at room temperature. So same thing, all the carbon's going to turn into carbon dioxide. All of the hydrogen is going to turn into water. There we have the 2 required numbers. Add up how many you have got here. You've got 4 O2s and another 2.5. That makes 6.5. Halves are allowed because you want 1 of those. Can do 6.5, that's alright. I just wrote 6 and a fraction, but 6.5 is acceptable as well. So that's kind of it when it comes to balancing. You can't balance, like I said just before the edit, you can't balance incomplete. You can only balance complete, which is why you have to have the atmosphere of enhanced levels of oxygen up to pure oxygen to get it to go. I will see you for the next bit of the video in just a moment. So what about trying to react alkanes with the standard sort of chemicals that you have? Nitric acid is renowned for doing lots of chemical reactions. Put it with an alkane, not a thing will take place. Sulfuric acid does quite a lot of reactions in chemistry. Not with alkanes, it doesn't. Sodium hydroxide, alkalis, just generally representing the alkali group. Not a thing takes place. Iodine, now I use iodine quite often for lots of reactions. No reaction. But don't make a mistake. The alkanes, particularly the liquid ones, hexane for instance, are good solvents. So it will dissolve iodine, but the iodine's still iodine, hasn't reacted with it, it's just gone into solution. That's because alkanes are non-polar. And alkanes at non-polar means it will dissolve non-polar substances reasonably well, like iodine. It won't dissolve that because that's ionic. So they'll sit as two layers, these ones here. The iodine will dissolve into the alkane, but that'll be the end of the story. Don't confuse dissolving for reactions. You are writing notes, aren't you? You should be stopping and starting me and writing notes. Good, you are. I'll see you in a moment. So, cracking, next thing. Now, you may well have done the cracking experiment at GCSE, where you took thickish alkane, it was soaked in some mineral wool, and you heated some bits of broken china, little bits of white shiny china, and you got some gas come off in mixed levels of success around the class, if experience is anything to go by. The reason you're using bits of china is china contains aluminium oxide, Al2O3, and you have to heat it, this catalyst. This is the catalyst, it's one of the examples of a non-transition metal catalyst. Has to be hot for it in order to catalyse the reaction. It is just, in order to get the reaction, a case of doing a little bit of adding up. You break the carbon chain. Now here I've produced alkene at ethene size. Doesn't have to be. You can even just chop off hydrogen. But it's large bit still saturated, small bit unsaturated. Here I've chosen 15 carbons, and it's a case of adding up. 15 carbons, 13 in the long still alkane part. There'll be 2 in the unsaturated short part. And 13 has 28, so take 28 off 32, there'll be 4. It adds up. Simple as that. You can do cracking where you end up with hydrogen and some other unsaturated molecule, but most of the time it's that. Thermal catalytic process, thermal decomposition. And you may well have done the experiment before, renowned for people getting like, don't stop heating until you've taken it out of the water and all that. Next thing we're going to look at is reforming. So I'll get the board clear for reforming and I'll see you ready for reforming. So reforming is because a lot of alkanes don't have particular uses. Unless you're going to set fire to them in a vehicle, then the uses are fairly limited. So you go through, in a chemical industry has reforming, you send them through a reforming process. And you use a catalyst to turn it into things that are more useful. So this is hexane. One of the things you can do is close the ring up on hexane, so you can make it into cyclohexane. But there's 2 hydrogens left over, so it produces hydrogen, which is of course a saleable product, especially with cars going over to hydrogen, some of them anyway. So this is a reforming process. You can then, as a chemical industry, take this and reform it a second time. I would imagine the catalyst is different. I actually didn't look up what the catalysts were. And you can produce this very important substance. This goes by the name of benzene. And it throws out 3 hydrogen molecules, gets rid of 1 hydrogen off of each carbon. And that is an incredibly useful substance because it's one of the feedstock materials for loads and loads of processes. Unpleasant chemical, but really important for things you can do with it. So it's taking something with relatively little use, hexane, reforming it into that, and then reforming it a second time into something much, much more useful. So it is really take the fractions out of fractional distillation, which is also part of the A-level course, but it is no different to the GCSE version. And I kind of think there are things you have to read for yourself. But reforming, well, reforming is new from GCSE. We don't talk about this at GCSE. And it's to turn relatively, well, molecules with relatively small numbers of uses into things that have much more uses. Now, the last thing that we need to look at is the most important one in terms of exam questions, which is photochemical substitution. So I'm going to get the board ready for that, and I'll see you when I'm ready. So, photochemical substitution. Now, in terms of exam questions, this is easily the most likely reaction of alkanes. We get whatever sort of question about it. Could be multiple choice, could be a long answer, could be just one of those structured questions. First of all, substitution. Substitution, exactly what it means in terms of sport. One off, one in its place. Hydrogen comes away, bromine takes its place, there it is substituted in. One of the hydrogens has gone and it's joined up with the other bromine. So the bromine doesn't both go in. One of the bromines is in, one is not in. So C13, that's rubbish. C6, H13, that's what I meant to say. H13 and a Br making the 14. Now it's an interesting reaction to do because it's quite spectacularly quick. Now, if you have two test tubes and you're going to set this little experiment up twice, now ideally I will be showing you that, but in my home I don't have these chemicals. So you have a small amount of the usual choices, something like hexane or cyclohexane, but this is for hexane, so you'd have hexane, a little bit, not much, just like a centimetre deep in two test tubes, and you put some bromine in. Not bromine itself, but bromine water in. It will sit in two layers when you do that. The bromine water doesn't mix with the water doesn't mix with the hexane. Put a bung in it, give it a shake. The bromine will dissolve into the hexane and it will be orange. But you need to be quite quick because of the way this reaction works. And then one of the tubes that you've set up with the bromine and the hexane, put it in a cupboard. It'll be in a test tube rack or it'll fall over. Put it in a cupboard in the dark or wrap it in aluminium foil if you prefer. The other one, go and hold it in the sunlight. If you hold the one in the sunlight, you can actually watch it very rapidly fade. The orange just fades away, fades away, fades when it's gone. It takes seconds. And last time I did this with some sixth formers, we took it out through the fire exit into the bright sunlight, and by the time they got out into the bright, it had gone and the colour had all vanished. It was that quick. So you bring the one out the dark, still orange. Put it back in the cupboard, leave it overnight, bring it back out, it'll still be orange. So in the dark, you get those. You get no reaction in the dark. For however long you keep it in the dark, it doesn't matter. It's the light that will cause it to decolorise in fairly quick time. So clearly the light has a role to play. Now we will come back to that in just a moment. So what you are doing in this reaction is you are using what part of the light? Well, the size of photon for ultraviolet, photon being a little packet of energy, for ultraviolet matches the bond energy for bromine and it will ping the bromine apart and you get two bromine atoms. Now the way to represent that you are expected to do is what's called half-headed arrows. So you do dance there for you. So you end up with bromine with an electron. So this really should have a dot on it. The dot represents an unpaired electron. Unpaired electrons are called, when they are not the electron but the species carrying the electron, called free radicals. Free radicals are notoriously reactive. They are the cause of ultraviolet giving you skin cancer. You get them in your skin with the exposure to ultraviolet in sunlight. Here, homolytically. Now homolytically means equal. So one electron goes to the left, one goes to the right. If you did 2 electrons to the right, none to the left, it would not be homolytic bond breaking, it would be called heterolytic. That's a different that's for a different thing, that's for a different reaction. I nearly used the word mechanism there, which is a word I haven't used yet and I'm going to use in a moment. So we need to talk about what's going on a little bit. So, like I say, this is all new to people at A level. Homolytic bond breaking produces free radicals. Free radicals are reactive species. They will not hang around. They will cause this reaction. Now, this reaction is what is termed the overall reaction. So I'm going to clear the board and show you a little bit more about what's going on. See you in a moment. Okay, so I slipped the word mechanism in accidentally in the previous segment. What a mechanism substeps. So when you look at how a reaction takes place, it takes place in a series of small steps. Those small steps, and there aren't usually that many, would add together to make a mechanism. So FRS is free radical substitution. Free radical substitution is one of, depends on your A-level course, 5 or 6 mechanisms you need to be able to trot out as an answer. One of the things about mechanisms is you need to be able to apply them to whichever molecule you are given, subject to its functional group content, that it's the right mechanism. So alkane, free radical substitution, you might be asked to do it to methane, you might be asked to do it to propane, you might be asked to do it to decane, it doesn't matter. The process of doing the mechanism is the same. Now, I'm not going to go into the details of the mechanism, I'll tell you why in a second, but the thing about free radical substitution is there are 3 types of steps. There is an initiation step, and there's only ever one initiation step in this free radical substitution that we are talking about here, and that is bromine. It could be chlorine, could be iodine. The ultraviolet turns it into 2 radicals. I've put a dot, a lot of science teachers or chemistry teachers put a dot. The examples say you don't need to have the dot. I recommend you put it in because it reminds you what you're doing. Now, propagation is there's a whole series of propagation steps, and I'm not going to go into what they are today. And there's a series of termination steps as well. As you might imagine, that ends the reaction. Now, the reason I'm not going to go into these 2 is that they're in a separate video, and you can, if you want to move on to that video, it's there ready to move on to. If you've got to the end of this one and you've made all your notes and you're happy with what goes on, you're then ready to go on to the free radical mechanisms video, and that one has some questions where you can apply your knowledge. Or you just want to take a pause after this, because this is all so much new stuff that you need to go away and assemble your notes. That's absolutely fine. This video up here was originally, it was filmed a while ago now, and it was filmed because I was producing revision videos for my 6th formers, and they asked for that during the first lockdown. So it does talk a bit about revision, but the content is identical. You just have to ignore the words about revision. And that's kind of it. I'll see you again very soon for some more. Don't forget to subscribe. Oh, I got told to say that today. And yeah, I'll see you for either you'll see me in the mechanisms for free radical substitution video or some other video very soon. Thank you very much for watching. Bye bye.